Okay, let's see. For people joining us, I am going to try and continue doing a bit of work that I was doing about multi-way systems based on numbers. And let me just show you, and this is relevant to Xerxes, who hasn't seen this, I think. Xerxes here?
Yes, I'm here.
Okay. So let's see, 2n, n plus 1. So that says, okay, let's start off from 0. Let's run it for, let's say, 5 steps. Okay, so this is a very simple multi-way system based on numbers. Red indicates the second one of these. I think blue indicates the first one. No, actually, the first one is red. Second one is blue. Okay, run it for a bit longer, and we get that kind of structure. Okay. This system is rather obviously confluent. Okay, there's a couple of different things I want to look at. I want to look at the confluence question for this system here. Okay. And I want to look at and then I want to talk about the continuum limit of these things. But actually, I have a point about the confluence of this. So what I'm realizing is that if you look at the total number of branches, so let's look at this thing here, and we look at the vertex in degree at this level. So this is a particular foliation, right? Vertex in degree of like 927, and then let's say count the number of in degree 2s. Those are the number of mergers, right? 6. But if we count the number of out degree 2s, they're 473. So there's a big mismatch. Like if we do the same thing here, I'm realizing, am I making any sense here? So if I go here and I say, let's say count of vertex in degree ag 2, and I believe that all of these systems have the feature that they only have 2 incoming. Ed, do you know that they only have 2?
Yes, that's the maximum.
For all of them. Is that obvious? Can you prove that?
Yes, it's obvious. Because out can only be red or blue, in can only be red or blue. And you can't have 2 blue edges coming in from the same number. Because basically there's only one way of getting n plus 1. There's only
but that's specific to this particular rule.
Oh, any rule system with 2 outgoings, there's a maximum of 2 incomings. Because you basically color the edges, and each color represents a unique number system. So if it's like times 2, there's only one way of getting to 8 with times 2, and that's starting with 4. So 4 is the only way.
That's a good way to think about it, actually. That each colored subgraph represents a particular quotes number system. But now, wait a minute. The colored subgraphs are not necessarily connected, right? Okay, so that's a question. Is the red subgraph connected? Answer, no.
Correct. But if you only started with one number and only one value, if you change that to nescrag tagged with just 2n, then it would be connected. You'd just basically be doubling the numbers.
Sure. That was just 2m. Right. And if we just had 2n there, I'm going to start with 0, which isn't very interesting, but otherwise we just have that, right?
Right.
So in some sense, and this is a Xerxes issue, this object here is some kind of product of these objects here. From a categorical point of view, what is that product?
Well, it's definitely not a sort of Cartesian product, right?
Right.
It seems to be it seems to be some kind of local application of how you apply these two rules together.
Right, but it's not a standard categorical.
Well, I mean, within the larger class of tensor products, you can define all kinds of tensor products, right? You have Kronecker products, which are tensor products. You have other kinds of tensor products. You can. So when we tried to previously look at simply taking multiple rules for multi-way systems in our ZX kind of operators, there what we identified was a non-trivial tensor product, which was obtained by simply kind of meshing two multi-way graphs in such a way that there was some identification of common states, etc. So again, over here, what I'm probably guessing is that if you were to take these two disconnected pieces, then what you're asking is, what is the operation you're doing to put them together? And this operation is some kind of identification or some kind of quotient operation locally, such that you get these two meshes to intertwine in this kind of rather non-trivial way.
I'd like to know if there's a way to do this, because I mean, this seems like it's a, is there a category theory way to write down how you get this from these?
Oh, I would say maybe the better question is if this should be something that might be graph theoretically or algebraically operationalized. You don't. It's not like category theory will give you a bag of products for this. I think what you're asking. For example, suppose these two subgraphs. Let's say I represent each of them just in terms of the adjacency matrices, and then I'm asking, what do I do with these two individual adjacency matrices to get this resulting matrix? And so there's a whole series of operations I would have to locally define to get this from these two initial matrices to the final one. So in a sense, the concrete place to ask this question would be at the graph theoretic level. And then later on, one might say that, well, this is some kind of non-trivial tensor where there is some quotient over common states which are being identified.
Can I jump in here as well? Because I think that I might have already. Hello. Hi.
Nice to hear from
Hi,
you.
Stephen. I think I might have. I think I might have studied this already. And there are some pictures that we could look at that illustrate the sense in which I think Quiver products can help us think about this.
Okay, it's interesting. So by the way, that's the adjacency matrix. There are two adjacency matrices that look like this, basically, and they productize to something that looks like this. Actually, I've never looked at that adjacency matrix, and I should look at an adjacency. I'm sorry to derail for a minute here, but then I want to hear about the Quiver things, but I want to see what happens here. So let's call this GR10 or something. There's this. And then uninteresting. What does that tell us? So, by the way, I don't even understand why some of those adjacency matrices, I mean, I'm confused by this picture, actually. There seem to be things which are not equal to 1 here, and I would have expected that there's nothing beyond 1.
Because that's telling you about the degree, the out degree and the in degree. So if you...
Why?
Because you're truncating this. So if you kept on doing it forever, then the out degree and in degree would be 2. Because you truncate it at some point, you don't give some of them a chance to, have their full out degree or in degree.
I see. Okay, fair enough. Hey, just before we quiver up here, and then I just want to check one thing, because I'm trying to look at Confluence here, and we have some ideas for how to compute it, and it's difficult because, like the branch pair 2131, we have no idea what it does. To give an example. So, I mean, this thing appears to be just going way out of control. Hold on, let me just make this That's the in degree. That's the out degree. And then what we want to do, and maybe there's a more efficient way to do this. How do we do the nest graph? Okay, a simple-minded way to do this would be to say that for t there, and let me do it first for the for this case here. So, for people who don't know, confluent means if there's a branch, like up here, if there's a branch there, then the two branches eventually merge, or not, as the case may be. Okay, so then here, let's make a table up to, let's say, t equals 10. Okay, there's very Fibonacci. Okay, so what that's telling us is the in degree, the total number of things with, that's actually, I should do it the other way around. This is the out degree. That's the number of branches. That's the number of merges at every given step. So that's actually an interesting result. So that shows us that for that rule, asymptotically, a fixed fraction of states will merge at any given level. Does that make sense?
Yeah, there's that asymptotic formula for the Fibonacci sequence that is
well, it's just
involves an exponential and a golden ratio.
It's just the golden ratio. This is just the golden ratio. Oh, look at that. So here, this seems to be sort of hopeless, right? Because the number of branches that are coming together, we might want to go on for a few more steps because we can't really tell whether that's going to be another exponential. Okay, so let's look at the two things here. So the first thing is okay, very, very close to 2. Okay, and the second thing may not be exponential at all. So let's say last slash at %41. I think it might actually be exponential. That looks rather Fibonacci-esque.
Find sequence function.
It won't work.
Is there some way of asking the OEIS? I mean, it feels like that should be built in, right?
Yes, I think there's a function repository thing, but we can, just type it in. But it's not. Okay, let's take a look at this thing though. I think that's going to be exponential, but let's see if we can get to another couple of terms. Should we want to live dangerously and go to 20? Let's try and go to 20. And let's monitor that just to see whether it's hopeless. Oh, it's going to work, he says. I think it's going to work.
How much of that count is just reflecting the total number of vertices that you visit? I mean, it's not the degrees maybe that's telling you about, it's just the total number of vertices.
Well, sure, but the point here is, when there's a branch, is there going to be a subsequent merge? And here, okay, so let's do, okay, very close to 2. And then, so that's very close to 2 to the n. And now last slash at % is those. Oh, look at that. Well, that's climbing a lot more impressively. See, because if that is exponential, if it's a fixed fraction, is that obvious? Wait a minute. If it's a fixed fraction, well, it's at least not hopeless. If this was climbing only linearly, it will be hopeless. It would never catch up. You'd never be able to have enough merges.
Well, hold on. I'm not sure I agree with that intuition, because that's true for any finite number of steps. But you could get something that trees out exponentially, but eventually it'll linearly catch up with itself, just at infinite time, so to speak. It's like the Hilbert's Hotel thing. Like, it's not, that would be true of a finite system, but Like so the precise claim would be that, sure, you can have exponential numbers of branches, but the merges might just take longer and longer and longer.
Look,
but
it's going to converge.
Given...
Listen, guys, it's going to converge to this is very interesting. It's going to converge to some number. That ratio is going to converge to something. And curiously, that ratio, I mean, could it be 3/2? That ratio. And by the way, I don't think this is going to be any kind of simple recurrence relation. But so that gives us some sense. This is very useful, actually. That gives us, I don't think it's hopeless, this thing. I mean, so let me just say, Ed had an idea, which is that turns out that every time there's a merger, the number at which the merger happens is of the form is equal to 31 mod 144. Does that sound obscure? No.
I didn't see it in any of the literature.
No, that's not what I was asking Tally and others whether that seemed like an obscure, I mean, let me see here. Just open up the thing that
grab the data, that icon.
No, I know, I'm going to do that, but I'm also going to look at, where is this? There we go. Okay, this was stuff from yesterday. That's different stuff, which we'll talk about later. Come on, where is it? So what we did, we have a derivation. The question is, one way, Tally, this is a good exercise. So we've got a computation. Here we go. Okay, so I have a version here that asks the question, given that we start off from, this is a computation of merging. Okay, so this is asking the question, given that we start off from the branch pair 9, 13, how long does it take to merge? Okay, so the answer, well, I actually am doing it in a stupid way here. Hold on one second here.
Literally, how long does it take to merge?
Yes. Yes, that wasn't the point. Hold on one second.
Empirical mathematics taken to the extreme.
Yeah, no, that wasn't my point here. Hold on. Okay, this is the thing I was writing. Let's see, somewhere here. By the way, this is a version of the same type of iteration of the 3n+1 problem. Is the same type of iteration. So they're closely related. Isn't that a wild animal there? Don't you like that one? That one is 6n floor n over 2. Okay, here we go. Where do I have this? Oh my gosh. Well, okay, so those are some branch pairs, and that's what we know about what they converge to. I'm very confused here. Okay, there we go. So those are what they converge to and how many steps they take to converge. Okay, so let's go over here. Those are some results, okay? But other branch pairs, like for example, 21, 31, we've been completely unable to tell whether they converge or not. Does that make sense? So one of the questions, this is for algorithmic cleverness, is can we tell? So Nick had an idea about, so what we've got is 2 trees. And I think I might have had pictures over here of what those look like. 2 trees. Yeah, so these are some of the trees, right? So the question is, you've got 2 hash plus 1, 3 hash plus 1. And the question, yeah, this is the tree starting from 3. This is the tree starting from 4. And the question is there ever an overlap in these trees? You see what I'm saying?
Is that enough? Because
All we need is an overlap. If we've got an overlap, then it's confluent. Then starting from a 3, you can find your way to the same place that you can find your way starting from a 4.
No, I get that. But there could be a way that you can get confluence that isn't just rule 1 applied several times and then rule 2 applied several times.
No. This tree is both rules applied all the possible times. Okay. Right? This is both rules applied all possible times starting from a different initial condition. The question is, do these trees intertwine? Do you see what I'm saying? Mostly those 2 trees are independent. Someplace
Can I ask why those trees never have any mergers themselves? Is that obvious? Why they don't merge themselves?
They do. They do. This one merges here. Oh, but you're asking why
3 and 4 never merge.
No, I understand. No, sorry. The tree that I was constructing down there couldn't merge. It's a tree. So in other words,
yes, but why is it a tree?
It's not a tree. It's a fake tree. It's a plastic tree. No, okay. I mean, it's in other words, what I did was I generated this as a tree, knowing that there were few mergers, just as an algorithmic thing. See what I'm saying? There are in fact mergers. You can see one right here. Right? The issue is whether the mergers that exist here, those 2 things turn out to be the same value, right? Even though those initial conditions are different, those 2 at that point in the tree, even though there are few mergers in the trees individually, those 2 happen to agree.
Yeah.
You know what I'm saying?
Here's a question. The motifs, so from an algebraic point of view, so these are quivers, just in case it's not obvious, right? The red and blue edges are cardinals, okay?
Mm-hmm.
So there's an algebraic relation that we see here, which is red, red, red equals blue, blue, at least locally for that tree at the top of your screen.
Mm-hmm.
And my question is the following. Is that path relation generally true? Is that a motif that happens everywhere?
Right.
What kind of merge motifs do we have in general?
This is exactly what we're looking at here.
Okay.
There are relations between yes, so we know that at the merger, right, it's always blue, red, blue, blue, and red, red merge. Okay. And that fact alone shows that the merger point must be equal to 3 mod 4, 7 mod 12, etc.
Okay.
Does that make sense? And what appears to be true empirically is that the merger point, so yes, there is some kind of algebra here of what. Okay, so a good question is what equivalence is.
Hold on. What I don't understand is that those little motifs you're showing, where's the fork, the original fork?
Oh, far up here. I can show you ones that have forked. There's one. There's one. That's the fork to 3, 4, and then it rejoins at 175 down there. But this one's covered correctly.
So an obvious question, maybe this is what you've already done as well, but then the next obvious question is there some kind of regular language that describes the words that produce these arbitrarily long...
You're good. I'm impressed. Yes. That was the next thing. Yes, there's a regular language.
Oh, okay, cool.
But yes, which we can construct some pieces of. And in fact, that was one of the things I was about to do. Okay, so let me just show you here.
One point when trees don't touch, it's called crown shyness.
That's a different kind of tree, Ed.
Yeah, but it applies here too.
That's funny.
Let's see. I don't want to.
The gift to many Instagram accounts.
Guys, how do I get this? I want to show this with the correct highlighting colors. Or does nest graph tagged have a highlighting Nick, how did that work with the highlighting colors for this?
That
Well, here, we can
was
just run
just
this.
rule styling.
Yeah, look, let's just do this. Oh, for goodness sake, that's not what I wanted. Oh, I need the subgraph. Wait a minute. What am I trying to do? I'm trying to find the subgraph of this graph. Help. Could somebody understand what are we doing here? So we're looking at this thing here, that original graph. Then we're saying, give me the subgraph of that graph, which is the find path in that graph to there to 175. But I'm now confused about why that isn't generating two subgraphs. What the heck? G to 175. Oh, very critical piece. Remove loose ends. I wonder if that has a more official name. That's removing all the trees on the edges. What's going on here? Okay, who understands this piece of code here? Oh, there's another important point. There we go. That's better. Okay, so there, tally is the I mean that shows some paths there, if that makes sense.
Yeah.
Actually, I just want to put in the
So there's a little interior bit that we don't care about, but
that's correct. Hold on a second. Let me just put this in here just so I remember it. Okay. That is the most annoying message. Okay, but anyway, so there are mergers like this. Okay, so now the finite state machine. So now you're asking what possible sequences can there be in the reds and blues and so on. Okay, so here's a fact. If we look at the same kind of thing, but we look at it mod, let's say mod 6. Okay. Then, okay, that finite state machine. So any number, right? Any sequence. This has to be, every sequence has to be mod 6 has to go in this order. Does that make sense?
Yeah.
So that tells us, so insofar as we've got to land on a particular number at the merger point, we know that every path, the reverse graph here gives us every path to that merger point, if I'm not mistaken. So for instance, if we pick up the mergers and we ask what mergers here, let's look at the mergers. I think we've got some results here. Okay, it's 3 mod 4. So let's say this is, if I do this mod 4, okay, the claim is that every merger point must be equal to 3 mod 4. So every merger point must get to that node.
why?
Because any merger point, 2u plus v 1 equals 3v plus 1. right? That's obvious. Because every number, if there's going to be a merging number, there must have been previous numbers, u and v.
Yes.
And one of them must have been multiplied by that. That's a red and a okay. So given that, let's see. So this implies that the number is odd. Okay, this can only be true if the resulting number 2u plus 1 is odd, I'm claiming. Why is that obvious? Is that obvious?
2u
Okay,
plus 1 is always odd, right?
Yes, that one's always odd. But my question is, for this identity, isn't there some Chinese remainder? Who knows the Chinese remainder theorem well enough to know what the collection? Somebody's asking nest graph tag. No, we just wrote nest graph tagged. It'll be in the function repository. Vittoria is asking. We can send it out to people if somebody wants to play with it.
Okay, so if I can, it seems like the strategy is something to do with, like, if you think about parity, just, residue modulo 2, then there's a kind of logic of the parity as you go back up from the merge point.
Mm-hmm.
There's an upward facing tree, right, which may itself have quote unquote mergers that are actually branches. And the upward facing tree, depending on whether you take red or blue as you go up, it kind of constrains you in terms of parity. Sometimes
you could also make there is a tree which is the inverted tree for this thing, right? You can make the inverted tree.
Yeah.
Just to be clear, let's see, we've got an inverted tree somewhere here. Yeah, I think this is now, it doesn't need that vertex delete, right, Nick? There we go. Okay, so this is the inverted tree. So that's kind of hacky the way it works, but that's an inverted tree, right? That has a branch point at 3, 4. Now, why the heck doesn't it? So if I go to 175, if I look at 175, okay, that will be the inverse of the thing we had up above here, I claim. Let's look at that. Is that in fact the inverse? Okay, the inverse 58, 87, 43, 21, 10, 3, 1. Okay, yes, that's the inverse. Okay, and the claim is that if you look at these numbers, mod whatever, the path, well, let's see, from a branch point, let's say this branch point here, we are following two paths from that branch point, 1, 4, 9, 19, this one here, right? That branch point corresponds to some particular path in that finite state machine.
Yeah.
Right? It goes from 1 to, go ahead.
So again, the Quiver technology is useful here. So that's a covering, it's a graph covering, right?
Okay.
And more specifically, it's a path homomorphism. So any path in the original multi-way graph becomes a path in this covered graph.
Oh, okay, that's an interesting way to look at it. Okay, so I was not aware of that technology properly. So let's see. So what you're saying is, all right, well, let's just establish for a second for what finite state machines, for any modulus, there will only be, well, okay, so for certain moduli, there will be a limited number of possible possible merge points. I mean, we looked at that. Let's take that, whatever it was, GR10 or whatever, and let's say vertex list vertex in component, I think it was called GR10, right? That will tell us, oh no, sorry, vertex in degree rather. That will tell us which things are mergers, are two mergers. Okay, so then what we want to do is we want to say position in that of 2, and then we want to say flatten that, and then we want to say vertex list of that. Oops, vertex list of G of that, of GR10 of that, right? And that gives us, those are the merger points, right, for that graph.
Wait, I want to understand what the strategy is. Is the strategy that there are kind of an infinite number of potential merge motifs, right? And you can get a handle on them by using this modulo trick to avoid.
There are only a five. Okay, and the claim is that those merge motifs form a regular language.
Okay. Wait, have you proved that?
Well, it's obvious because once you know, right? Here's why. Okay, imagine that you're doing mod 12. Okay, so first point is, okay, let's walk through this. Okay, so first point is, let's get a bigger version of this. Hold on one second. I need to get a big version of this thing. Hold on. Let's get rid of that. Okay, so this should be a list of merge points. Okay, that's a list of merge points. Now, let's look at that table of that list of merge points, mod K. Okay. K goes up to, let's say, well, actually, we know it's going to have to go a long way because we know mod 144 is interesting. So let's say to 200, and let's select. And let's select ones for which length of last of hash is less than 4, let's say. What did I do wrong? Oh, I want to say union here. Okay, there we go. So this is showing us those moduli for which the merge points appear to have a pretty fixed form. Does that make sense?
Yes.
Okay, so now.
Couldn't you do a histogram or something?
For what?
Well, like you're trying to say, is the residue like strongly preferring? Is there some, you know, if you pick the right modulus, is there one?
Yeah. Okay. So let's do that. That's an obvious thing to do. So let's make a histogram of. Actually, it's not even a histogram. It's just a bar chart. Just a list. It's just a list step plot of length of union of mod %64, K. Table of that.
The length of union is not going to say how preferred it is, right? It's
no. Okay, that's a different issue. I agree. That's a different issue. Okay, so there, what we're seeing is that certain moduli have a small number of possible things, small number of possible cases. Yeah. But what we could also do is we could say
entropy. Use entropy because that's gonna strongly favor things where.
I hate that. Let's just look at the case of, let's say 144. Okay, so let's say mod %64, 144, and let's look at the histogram of that. What? Oh, there are only two modules. That's right. There are only two values. See what I'm saying? So for most values of k, like if I pick 142, for example, there'll be all kinds of different values. But for 144, there are only two possible values. Does that make sense?
Yeah.
So Ed,
I mean,
I'm surprised that there's a value. So most of the time it's equal to 31 mod 144. Most merge points, that merge point there may be a trivial merge point.
Right.
So therefore,
I think that's the 0 merge point.
Oh, yeah, let's try starting this from 1 here. Oh, you're absolutely right. You're absolutely right. That's a better case. Say. Oh, this is much cleaner. Good suggestion. Okay, so now that one is going to be like this. Oh, for goodness freaking sake. Oh my goodness. My goodness. No. What a dopey thing. Okay. 0 to 144 automatic. Okay. Great. But now if I do this, it'll be all over the place. Okay, so this is a place. So 144 is something for which there is only a single value. Okay, 72 is another one. That's interesting. Look at that. 48. So come on, Chinese remainders, people. What numbers isn't who knows how the Chinese remainder theorem works? This is a quintessential example of that, I think. Boy, come on. Somebody has a Ed, surely you know.
Yeah, well, I know how to set up Chinese remember problem. I'm not sure how to carry this into that.
Okay, but so the question is, what is the condition here that, so we got a whole bunch of cases here where we know there's a unique value, right? Where we know there's a unique value mod whatever it is, right? Or whether there seems to be a unique value mod whatever. Okay, so let's try doing this. Say this, and then let's go up to 1,000 just to see how many more there are. Oh, look at that. That's the last one.
So it feels like the most principled way to think about this is as a Fourier transform, right? Like discrete Fourier transform. So by searching for the particular residues where, where vertices are constant, where mergers are concentrated, you are just finding peaks in the discrete Fourier transform of the mergers if you see them as a sequence.
I guess. But look, the main thing, we don't know why this result is right, although it's probably a Chinese remainder type story, okay? Because that is a bunch of relations between, there are a bunch of algebraic relations, and this will give you, okay, so these are the residues, these are the things which are well defined. Okay, so if we take 144 as an example, right, and we go back up
72 has also got as strong a signal. I mean, 144 seems like it's too big.
Well, okay, fine. We'll look at a smaller one, but it doesn't matter. We'll look at let's look at 18, for example. Okay. Okay, there's a finite state machine. We know that everything must end. That the only way there can be a merger is if you hit a 13, right? So therefore, if we start with a particular number, so let's say we start with a number, let's say we start with 4 and 3, okay? 4 mod, so 4 hits a 13 there, 3 goes 3 things to hit a 13. Okay, so let's remind ourselves what it actually did. So here's what it's doing. So now let's look at what happens. So we start with a 1 here. What did I say we started with? Okay, we start with a 1. It goes to 3 and 4. Okay. So now 4. Okay, that 13 transition is not the 13 transition we're actually going to use. Okay, instead we're going to use the transition that goes red, red, blue, blue, 13. See what I'm saying? A different path. But any path by which it reaches, so 13 is the acceptor state for the finite state machine. You see what I'm saying?
Yeah.
And what we're asking is any word, so in other words, if we start with a given thing and we want to know whether there's a merger between 3 and 4, we don't need to look at all possible sequences of reds and blues. We only need to look at the reds and blues that are in this finite state machine.
Hold on a second. So one thing should be obvious, which is that you can't take a path in this finite state machine and lift it into a path in the multiway graph, for the obvious reason that some of those paths just don't correspond to paths in the multiway graph.
That's correct. This is
Right? That's what coverings do, is that they make fictitious paths.
Right. So your point is this can be thought of as a covering of the multiway graph which supports additional paths that aren't real.
The language is opposite there. So the multiway graph covers this path, this graph.
Okay. So thought of as being covered by the multiway graph.
Yeah, and it's sorry to make you use my brand, but it is a Quiver covering because it has to preserve colors, aka cardinals. It's not a graph coloring.
Okay.
A graph covering.
It's a tally style Quiver covering. Because it preserves the colors.
Right.
Okay, now let me point out something. So normally we've got 2 to the n, the number of numbers from starting from 1, the number of trees is 2 to the n, right? But it isn't 2 to the n because it's actually only the paths in this graph. But to compute the number of paths in this graph, we can use code that's even in the NKS book that computes the entropy of a regular language. Right? The entropy of this regular language is given by the eigenvalues of the adjacency matrix here. If I'm right, you see what I'm saying? Because
how does that work?
Okay, the point is this. I have to look up the NKS book.
So, I mean, one thing that kind of seems plausible is that if you pick some cycles in this graph, then you can make a regular language for paths in the graph out of those cycles, right? Because
no, here's the point.
Long enough.
The point is there is okay, in these things, these are finite state machines that represent all possible states that can be gotten by a cellular automaton, and it's the same story as these. And the entropy of this, yeah, so that's an interesting thing. Excluded blocks is one interesting idea. That is, there are certain blocks you can't have because of this graph. See what I'm saying? If the graph was just like 2 ears going back to a single state, you could have all possible sequences of reds and blues, but you can't in this case.
Yeah, that's why it's a groupoid.
As opposed to
it's really what, as opposed to a group. So the 2 ears thing is called a bouquet quiver.
Okay. Well, here, look, this is okay. So this is the number Oh boy, we still had apply plus. We didn't have total back in those days. Okay, so this is the number of paths of length n in the adjacency matrix. So the adjacency matrix so let's say we go table. Okay, so that's the number of possible paths in this graph. Noting, I think that's from all possible initial conditions. So that is to be compared with, let's go up to 20, and then let's do the following. Let's say, well, the largest eigenvalue, what the heck is that? I hope I'm computing the right thing. Let's see. Let's look at ratios here. This should give, that should give the oh, that's very disappointing. Maybe I'm computing the wrong thing here. That's just doubling every time. I think I must be computing the wrong thing. I think this matters. I wonder what net is. Adjacency matrix. What is that? Well, do you understand? You understand that there's a, okay, we need to figure out how to compute this.
Okay, so if you raise the adjacency matrix to n, then the ijth entry will count the number of paths from vertex I to vertex j. That makes total sense. That's really easy.
Yep.
Then of course, if you diagonalize the adjacency matrix, then you can do it quickly. And you can also do it in a closed form.
Absolutely.
Because of the eigenvalues. So
right,
then it's the trace. Yeah.
That's the traces, the ones going back to the same state again. They're
right.
Closed paths.
Yes.
That's related to zeta functions for the finite state machine.
For
so
the
what would be, yeah.
For that path count, does that include paths that contain cycles?
Yeah, of course it does.
Okay.
Which is what you wanted. I know, Ed. You
right.
Were that. What you want, and we should just write code that does this, and we can just compute. Look, the number of paths. Look, it's the number of paths starting at 1. Okay, so that's actually multiplying the adjacency matrix by a particular vector. Right, let's get rid of the stupid 1, 0. There. Well, I don't know whether we can get rid of the 0. Oh, we can. 0 doesn't show up. That's nice.
Shouldn't you make that 1 be actually range 1 to whatever your modulus is? Because why are you assuming that you're starting with residue 1? You could start with any residue.
Well, fair enough. Okay, so let's just do range to 17. Harumph.
So just take a step back. We're counting the number of paths. Why do we care about the number of paths for this particular question?
Because we're trying to figure out if, okay, the most natural way to enumerate, to figure out whether two possible tentacles starting at 21 and 31, for example, whether those tentacles can ever join is to tree out all possible tentacles. That treeing out is a 2 to the n. For tentacles of length n, that's 2 to the n things to tree out. Okay?
Yes.
The whole point here is, if this is a small fraction of 2 to the n, if the entropy of this graph is much smaller than 1, that means it's 2 to the power entropy times n. And if that entropy is small, that as a practical matter allows us to do much less treeing. You see what I'm saying?
Okay.
Right, so the question then is, what is the entropy of this graph? But what we want to know is the number of paths that end in state, what was it? This is size 18, that end in state 13. Okay, 13 is the acceptor state, right? So it's the number of paths that go to state 13, right? You know, we should have something in the graph framework, or somebody should write it as a WFR that counts the number of paths from node A to node B of a certain length. We don't have that, do we? Or can we do that with, no, because find path doesn't deal with cycles, right, Ed? Ed?
Yes, that's correct.
Okay, so what we want to know is how many paths starting, e.g. at 2, at 3, of length n, end in 13. Okay.
You can do that in it's a one-liner though.
Yeah, I know it's an adjacency matrix. So let's just do it. Right. So that is matrix power. Okay, so let's say is this a deterministic finite state machine? Yes, it is. Yes, it is. Okay, so matrix power of the DFA, let's say of the adjacency matrix of the DFA. Okay, so there's our fine matrix power. Now we want to take that dotted into element 13. Well, it's actually element 14 because it starts at 0, right? Is that right? Do you understand what I'm saying? So this should be dotted into replace part.
Well, unit vector, just unit vector of the ith, and then on the other side, the unit vector of the jth. But
okay. No, wait. Unit vector. What? How does that work? It has dimensions. In the kth direction. Okay. N-dimensional. So that's unit vector 18 in the 14th direction. Right?
Yep, and then on the other side with the target, but you'll need to make it a column vector.
No, I don't need to because we have the lovely feature that this will. The unit vector is that automatically works. So let's say for 3 there. Okay. Okay. All right. So now let's look as a function of n. We can look at how many paths there are and see how that compares to 2 to the n. Okay, let's continue it a bit longer. That's unfortunately getting very big. I don't like that. Oh, for goodness frigging sake.
Why aren't you dividing that by 2 to the n though? Because it's the fraction presumably of paths.
Well, yes, okay, fair enough. I mean, okay, fine. Well, we can do that, but let's do it. And this is going to tell us how much better we do here than we do by just doing a raw. Okay, so we do 30 times better at the end. Well, that's worth having. Oh, we do 30 times better, which is probably not surprising. But let's now look, just for the hell of it, let's look at the corresponding thing with size 144. You see what I'm saying? Because that's the other, that's the largest case we know. So that should give us the best factor. Okay, there's our finite state machine. And now this wants to be, so it's equal to 31, which is the 32nd element. 31, 32nd element here. Oops, that's 144, and that's the 32nd element. And then this is 144, and that's, oh, you know what? I had the wrong thing. I had the wrong thing here. It's actually not 3, it's actually 4 that I care about there. Is it going to give exactly the same result? Basically, yes. Okay, so here, all right, let's see what this gives. What did I do wrong?
I posted some code in chat.
Wait. We're solving this problem first. Well, that's very uninspiring. Look at that. It doesn't make any difference. So the size of the pruning that we get from this thing is the same as the pruning we get from this thing. Well, let's just try an even much simpler one. Let's try.
There's more pruning you can do.
Okay.
I posted the code in chat.
Okay, but hold on, Edward. Just working through this. Okay, let's say size 6. Okay, let's just see what the corresponding thing is for size 6. All right, very simple DFA. Okay, now it was equal to what, mod 6? Mod 6, it was 1, which is the second element.
You'll need to redo all this soon.
I'm going to do this first, then we'll redo it. Is it wrong, what we have here?
Yes.
Okay, all right, let's see what Ed has.
You can basically just start with 1. And the code I've put in basically shows that all cycles eventually cast out and you can just stick with 1.
Could you please start using automatic rather than quotes name? We made that change like 5 years ago, Ed.
So that's the graph if you use everything. And if you change range 144 to 1, you get the exact same graph.
So what? I mean, that's nice.
So all these cases where it matters, having extra numbers in there, they don't matter because they all get cast out quickly. Everything.
Yeah, that's fine. It's fine. So you're saying if we go here, if we start this off from 1 there, it's a different graph.
Right, because there are various elements that
I see. These things are trees effectively that go down onto the cyclic part of the graph.
Right.
Okay, but it's not going to do us any harm to compute. The computation we did is fine. It's just that there's some superfluous pieces which don't affect the long-term behavior.
Correct.
I mean, the problem with this argument is that some of the paths are fictitious, so you can't actually count them. But I think there's a nice way to think through that.
No, but Tally, what we were trying to do first, we know this is the first thing we're trying to do is just the pure experiment of can we can only get to things that merge after 19 steps. If we wanted to find something that merges after 82 steps, we're just out of luck because 2 to the 82 is just way too big, right? So the question is, what techniques can we use to prune? What this is showing us is that we can get a constant factor of about 30. Okay.
So the overall aim is to speed up the computation of merge points.
Yes, that's right. Now, a better scheme would be to ask the question, is there a different strategy? This is saying that any merge point, that there's a grammar of what paths you need to try to find a merge point. Now, the main issue is right now we are doing something where we are essentially treeing out lots of possible paths, right? This is reducing the treeing. And what we want to do is instead of treeing, what we want to do is we want to find all possible paths to depth. Okay, this is a straightforward piece of recursive code. We just need the paths that you can get to by you know, we just need all possible paths up to size whatever that go through this graph. Am I making sense? From a given starting point. And then for each of those paths, we evaluate what it actually is. For any given path, we decover it, so to speak, to get to what it actually was in the multiway system. See what I'm saying?
Yeah, homotopy lifting.
Okay. Okay, so for a given path, we do, that's very fancy sounding, homotopy lifting to find out what the path would have been in the multiway system, in the multiway graph. Okay, so this is just a practical matter of, okay, can we write, is it super fast to write the code that will successively get, let's see.
The matrix power paths.
Yes, but what we're trying to do, okay, here's what we need. Given a DFA, like, I don't know, we don't even need the biggest DFA. We were getting the same speed up with the size 18 DFA. Okay, so just that original DFA. Given this original DFA here, okay, our friendly DFA there, okay? And you're saying we can actually, well, let's not prune this DFA. We don't need to prune the DFA. It has leaders in it that go from like 8, which is a transient. Okay. What we want to do here is we want to just start enumerating what possible steps there are. So what we get is at a given stage, okay, I see, it's just powers of the adjacency matrix, right? So we say for the adjacency matrix of the DFA, we are yes, we have a certain set of every, we're just asking, what does it map? Well, alternatively, we can turn this graph.
There's a thing called graph power, which takes a graph to the same graph, but where the edges represent paths of a maximum length.
Okay, so what we're saying, what are you saying? We're saying graph power of DFA, 3, for example, for whatever. That's nice, but I'm not sure that's necessarily relevant. I mean, what I'm thinking is, what we're trying to do is at every stage, okay, so normally, okay, let me point out, normally what we do is we've got this nest graph, okay? So if you look at my code, wherever it was, for finding, here we go. All this is doing is a nest while list, okay? So given, okay, this is the minimal code. You see this code? This is simply doing, so we can improve this by a factor of 30 by going, look, this is what this is doing is, it's just saying, given a set of values from one of the members of the branch pair, given a set of values from one of the members of this branch pair, just apply this 2n plus 1, 3n plus 1 thing, just apply both of those things to every value. See what I'm saying? But really what we want to do is we want to have a list that contains a value and the DFA state, right? And then we only need to, instead of applying both of these, we only need to apply the things where there is, okay, so in fact, here's the way to do this. This is much easier. There's a much easier way to do this. Okay, given the DFA, we get the edge list of the DFA. Okay, now what we're going to say is, for each one of these, for any given left-hand side, how many, yeah, this is going to tell us how many distinct destinations are, why this isn't reducing very much, right? Because most things have a right-hand side. I don't get it. I don't see why this helps. Do you understand what I'm saying? So in other words, if we record for a given number in the multiway system, both what that number is and the representation of history about what DFA state it reached, then what we want to know is, do we need to consider both possible things the number can happen to the number, the 2 multiplication and the 3 multiplication, or less than that? Because it should be less than that, because the did you get what I'm saying?
No, yeah, I get what you're saying, but so here's the modification to the idea, right? So find, here's what you do. You know that you're going to eventually end up at whatever it was, 17, or what was the magic thing?
Well, in this case, it was, I forget, it was...
Yeah, whatever, the sink. It's the merge vertex, right? So the shortcut is that you can pre-compute a whole bunch of paths that take you from other vertices to the merge vertex. Those will give you words of the form red, 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 blue, blue, and then another one, blue, blue, red, or whatever, right? And so those things, you can even turn those into little polynomials that just pre-compute the jump going straight to the target number.
Yep.
And the point, some of those paths will be quote unquote fictitious. They're not going to give you, they're not going to do nice things. But if you just, apply that list of functions that have been pre-computed to a given, merge point, then you're going to want to find a conflict in that list. You're going to want to find a duplicate in that list. That'll be a merge.
But I don't understand. Look, the point is, the thing I just described, where you say value in DFA state, that's the iteration at every step. Because normally, in this case here, see what I'm doing? I'm just doing the 2 to the n, or 2 to the t. I'm just generating 2 to the t cases here. You see what I'm saying?
Yep. But Stephen, here's the flaw. I mean, the reason that it doesn't save you anything to do it this way is that the number of paths in a small graph can be as large as the number of paths in a big graph, right? Like you don't save on the number of paths, because at each vertex, you still have roughly the same number of choices. In fact, in your DFA, you sometimes have more than 2 choices.
No, you
like
don't.
Sometimes,
no, you don't. It's
2
a DFA.
Yeah. No,
then it's not a DFA.
Well, take a look at it. Then it's not a DFA. I mean, take a look. It's got 2 outgoing red edges in some cases. I mean, look at the picture, not at the list of rules.
It really shouldn't have.
Okay, wait, sorry. It has 2 incoming red edges in
That's
some
correct.
cases.
Shouldn't have 2 outgoing, otherwise it's not a DFA.
But in any case, there will always be a red and a blue coming out, right? And that means that you still have 2 to the n number of paths starting at a given vertex. So you haven't saved on the number of paths if you're going to still tree them out. So you shouldn't tree them out. You should exploit the fact that you know that they have to conflict at whatever it was, 7, or whatever the magic thing was, right? So pre-compute a bunch of paths.
I'm sorry, I simply don't understand. The regular language that this generates, unless this DFA is not minimal, if the number of paths through this DFA is 2 to the n, okay, then this DFA is equivalent to the trivial, whatever you called that. You had a fancy name for it, bouquet DFA.
Yeah.
See what I'm saying? So that's the question. What is the minimal DFA for this DFA? And
I think you might be thinking of the number of states rather than the number of paths.
I am. I'm asking, is this DFA equivalent to the bouquet DFA if you merge states? If the answer is yes, then this will save us, well, okay, it might save us something.
And I can categorically say it is yes, because you simply contract all vertices together into one vertex, and then all red paths become one red path, all blue paths become one blue path, and it's the 2-eared 2 bouquet.
Are you telling me that every one of these vertices has 2 red and 2 blue coming out of it?
1 red and 1 blue.
Yeah, right.
Yes.
Okay. So look, bottom line, this is going to save us a factor of 30, but we've probably been discussing it as long as that anyway. Is there any better idea?
I've been saving something, but it's not the broader strategy you were talking about. So maybe I can describe it, and then if you don't have to pursue that, it's just, I think it's an interesting thing to think about.
Yeah.
So it's a theoretical thing. It's not a code thing. So the claim would be that if you want a guaranteed way of coming up with a path, we know that you can't take one of these guys and lift and just say, oh, we start at a given residue and we just choose two paths in this DFA and it'll give you a merge. It won't give you a merge because all you've guaranteed is it'll give you two vertices that come out of the starting point that have the same residue, modulo, whatever. Not that they're the same as
indeed,
right, yeah. But imagine a whole family of these DFAs for different classes. And if you have a conspiracy that you can find a path.
I understand. That's like the Hensel lifting lemma for factorization. When you factor
on that? I've never heard that before. What is that?
When you factor a polynomial, the way you do it is you factor mod a series of primes. And if the factorization agrees, and you factor mod a series of primes, when the factorization problem becomes essentially a numerical factorization problem. And there's this lifting lemma that guarantees that if you've successfully factored over enough primes, then you factored over the integers.
Okay, that's really cool. So that was exactly my suggestion here. And it connects to modular representation theory, at least in the way I'm thinking about it in terms of quivers. And the idea is that the multi-way graph is the true object.
Mm-hmm.
And then you have all these coverings of that into these simpler descriptions that are imprecise. And they're imprecise because they only talk about residue classes, right?
Yep.
Then the claim is, the reason I'm calling it representation theory, modular representation theory, is that the claim is that if you take enough of them, then the direct sum of vertices from each one completely recovers information about the original multi-way graph.
I get the idea. Right. I mean, that would be the analog of this lifting lemma, that you can get it over the integers. You can get factorization over the integers. So, but what we know from this thing up here is we know the set of residue classes for which there is a unique merge point thing. At least we think we do. I mean, this is just an empirical thing. And for all I know, there could be merge points that are exceptional merge points. I don't think so.
But then they're easy to check because because the idea would be that even if you take this list that you've got here, then you have to find coincidental paths that match in all of them and lead to the magic residue class in each of them. And once you've done that, you've got a general recipe that's very fast to try for a given vertex in the multi-way graph. Maybe it'll sometimes fail because of some exceptional thing that's not in this list, but presumably it'll often work.
Well, you're saying from 3 and 4, for example, could you ever fail in these graphs? Okay, so this is the question. Could it ever fail to get to the sync point? I don't think it ever fails. I think these graphs are ergodic.
Yeah.
That is, I think there exists a way to get to the sync point from any vertex here.
Right. So here's the recipe. You've got a vertex in the multi-way graph that you want to find a merge from, right?
Mm-hmm.
A merge point, the corresponding merge point.
Yep.
You've got a fork point and you want to find a merge point. So you take its residues, modulo, 1, what are these things? 2, 3, 4, 6, 8, 9, 12, and so on. Right. And then in each of those, you enumerate paths up to a given length that start at the source.
See whether they agree and see whether they agree and manage to get to a sync point by that point.
And you just take an intersection of those guys. That's very fast, right? Once you've done that,
you can probably generate a single finite state machine that does the whole thing. Like just taking the direct product of the finite state machines for each of these moduli.
Right.
That will be essentially a parser for any. So what you do, the combined finite state machine, right? Combined finite state machine, combined DFA, every node, every vertex is a list of n mod m1, m2, m3, etc.
Right. So, but more conceptually, every vertex is a list of vertices in each of the smaller DFAs.
Absolutely. Right. I'm saying you could direct product the thing, and that way you would get a single DFA. And the question is, okay, so this is
but you wouldn't want to compute it that way, because that super massive DFA is going to be quite large, probably near as large as the original multi-way graph, right? Okay. So what you'd want to do is solve the find all parts problem for each sub-DFA, because you can solve parts up to whatever length, and it's quite cheap to do it in each sub-DFA. And then you just intersect the words of those parts. That's also cheap.
Yeah.
And now you've got a word for the super DFA or for the
right. So then the goal is to find the intersection word, which is a possible word to actually reach a merge point over the integers. Right?
Yeah.
Ed, did you understand all of this?
No.
I can. Is Ed actually working on this problem with you, Stephen?
Well, that's the idea. I mean, I'm trying to get this done quickly, so this is like a today's issue type thing. But I think I understand what I mean. Look, I think the thing we need is a piece of code that, given a DFA, finds the next state. The DFA is just a set of rules. We can just dispatch on a set of rules, and it tells you for every one of these, it's going to give you what the next state. It's going to tell you, given a state and a symbol, it wants to tell you the next state. Actually, is that what it wants, or does it want to give you? Does it want to tell you a path? Oh, I'm confused.
What's really, really cool, Stephen, is that this really is representation theory, right? And so selecting, for example, selecting these projections or coverings, some of them are going to be redundant. They're going to be like copies of other ones. And that really is the same idea as representation being irreducible or not.
I understand.
So what's cool is that not only is this a computational thing that will help us find merge points, but if you can prove on purely theoretical grounds that list finally terminates, then you've got like a general proof of confluence in the system that doesn't depend on any computation. It's just a decomposition.
Yes, I understand. Or non-confluence, as the case may be.
Yeah.
All right, this is nice. I think we should switch topics because we don't have that much time. I really want to cover one more thing. And I can send this notebook out. Oh, so much for me finishing this today. Still might. Okay, before I forget, let me just send this to you, Tally, at the very least. Okay, let me tackle my next topic. Okay, my next topic is, imagine these systems. I want to know what the limit of a multi-way system, what the continuum limit of a multi-way system is. Okay. So the question is, what's the analogy? Okay. So, all right. So we have a multi-way graph. For example, let's pick our favorite random multi-way graph. Let's say this guy here. Okay. Question is, what is the continuum limit of this? In other words, what would a continuum limit be? Continuum limit would presumably be, instead of picking a finite number of branches here, we pick an infinite number of branches. Am I making sense? So what we want to pick is probably an infinite number of branches. And then the other degree of freedom is branching infinitesimally, branching infinitely often. Okay, my question is, how does this relate? Well, so there's graphons, which are the limiting case of a graph. So a graphon would be, just as we can take the adjacency matrix for this guy, we can ask, what is the continuum limit of that adjacency matrix? Am I making sense? So this thing, for goodness sake, matrix plot. Okay, so we can ask this thing becoming a function of
continuous interval 0 to 1.
I mean,
yeah.
The problem with that,
would be smooth lines of some kind. Like those would be 3 smooth lines.
Yes. I mean, the problem with that, let's see, there was a nice thing. Michael sent this to me. Hold on one second. There was a notebook about graphons that somebody produced. Here we go. Graphons. Okay, a graphon is a symmetric Lebesgue measurable function from 0, 1 squared to 0, 1. Yes, I agree. The cut metric. The heck is that? 2 graphons that we will use. Okay, square root of x times y and 1 minus max this. Okay. So what this is telling one is, so let's take one of these graphons, 1 minus max xy. So what that's telling us is from a given, that is telling us from a given x value, which is essentially a point in the graphon, it connects to a point y. This is just telling us for any given, wait a minute, why isn't the issue, the connectivity, given a continuous function, why isn't it just oh, I see. This tells us that essentially the density of connections from one point in the graph to another point in the infinite graph.
And speaking of that, it looks like your matrix plot shows that those 3 lines are not actually going to have equal density. It looks like the bottom one gets less and less dense as you go to the right.
Right. So the limit of this thing, noticing that the limit is totally undefined because the ordering of these nodes is arbitrary. Well, actually, it's not arbitrary. It's not arbitrary. Yeah. This is an important point. For us, the ordering of nodes is not arbitrary. It is for ordinary graph. Is not arbitrary. They are specific numbers.
Right. So a naive question, Stephen, is why can't you just take your existing definition of 2n plus 1 and 3n plus 1
and make it a function?
And just interpret it as a function over the real interval, 0 to 1. Like what will happen? It's a multi-function,
that's a good question.
Right?
Right, that's a good question. So this becomes this thing here. Well, where's the 0 to 1? Why is it 0 to 1? N is an integer, is an unbounded integer here.
Sure. To be a graphon, it has to be from 0 to 1.
I know that, but I think there's a more interesting case here because this n could be a real number. And let's imagine here, let's imagine the following thing. Okay, I've got an idea. So let's do a nest list here. And let's say, instead of doing this, that we say from from, let's say, 0 to 1 in steps of 0.02 or something, okay? The problem is that there'll be very, very few mergers. This will just be a spray of stuff, right? If this is, well, look, if this is, let's say this is 0.1, well, let's just say it's 1/10, right, to be accurate here. Okay, so now we'll say 3 steps, for example.
Oh, because of the +1, yeah.
But look at this. So what we want to do is we want to say, what am I doing? I want to nest graph this, in fact. Oh boy. So the question is, what's the limit of this? So as I change that 1/10, well, maybe it has a limit. Wow, that would be interesting. So you understand what I'm saying, that these numbers here, I could plot. So if I do vertex count, vertex list here, okay, they're actual numbers, right? So I could make a histogram of those numbers. Right, so that's an interesting issue. If I just iterate this thing with real number pieces, what is the distribution? So noting that there will be some mergers. Am I making sense? I mean, in other words, the number of numbers there will be %117. The number of numbers is less than, it's not a tree. We can see it's not a tree. Here, it's obviously not a tree. So a question that we have is, as a function of this, as a function of the 1/10, actually what we could do, this could be a nest graph tag perfectly well. Right, and now what we want to do is, as a function of the 1/10, let's say we go to 1/20 here. Okay, the question is that going to have a limit?
By the way, there's a nice grid. The bottom connected component is a large chunk of it is a nice looking grid.
It is indeed. Oh dear. Okay, so this is some weird number theoretical thing, presumably. If we say 2n, okay, let's just start off with a much more naive thing. Let's say we go to n+1, n+2. That's a very trivial.
It's going to be a tree. It's going to be a grid.
It's going to be a grid. Okay, so each one of those is a grid. Because that's a +1 and +2, they can't, each one of those grids is offset by 1/25th because it can never regain itself. If, on the other hand, if this number here, actually after sufficiently many steps, it will regain itself. If that's an 1/8, I claim, if I go more steps, let's say I go 9 steps, I'm wrong. I thought these were going to, you see what I'm saying? I thought these were, so now if I make the histogram,
oh no, go 10 steps. It's because 1/8 doesn't divide 1. I mean, what am I saying? It does divide 1.
Well, that was boring, but okay, so this, but I claim that this thing here, the n+1, 2n, I think this is going to wind up, I don't know how big this is going to be. That might be, oh, look at that puppy. That's a very elegant creature. Okay, so that.
You do it in 3D. Does it become a kind of funnel? I mean, kind of.
Kind of. I mean, that spiral is the +1 spiral. And then this is the, and what's happening here is just that, yeah, things agree. The 2n, that 2 is commensurate with the 8. So if I predict if that was 1/7, this thing will look different. This thing will have many more points if that's 1/7. Okay, those are different, essentially what amount to different residue classes, I think.
Yeah. And if it is irrational, then they would never.
Right, if that was irrational, well, it's going to be hard for us to do that, but we can try. For example, let's do 1 pith here. Actually, let's just do 1/√2, okay? And then let's do here, this is really dangerous, but let's do this. And let's do like 4 steps. Oh, it can't be 1/√2, it has to be 1/√, of, what's a good number to pick that's square root of 8 or something. Okay, wow.
Well, that's only 4 steps. Maybe.
What the heck is going on here? 0 to 1.
What is that range? Just out of interest.
Yeah, what is it? Oh, it's just 3 numbers. But I think if we go,
I mean, you need more than, that's the total number of seeds, right? So you can't, and 0 is sort of trivial, because 0 will just jump to 1, and 2 and 0 will stay 0. So
I see. So your point is that there's a limited number of seeds. And the fact that this is, so each one of those seeds, you claim, will pretty much make
another component, yeah. So
well,
if you try 0 to 3, you should have 4 different components or 3 different components.
Well, we're getting 3 times as many components.
Yeah.
Right, but why are those components? Each one of those components has a doesn't have the usual spiral structure. Is this thing somehow irregular because it's digging into the digit sequence? I think it is.
Well, there's also going to be the fact that no. How can it do that? That's just an offset, right? Oh no, wait. Normally those guys would connect up. I bet you the left and right sides would connect up because the n+1.
Yeah, exactly. That's exactly right. This thing here is going to be a big mess. If we go like 12 steps here, wow. Okay. So this is a more complicated lattice leaf, I claim. Yeah, it no longer has the regularity that it used to have. That would normally be
I wonder if there's a connection to the p-adic numbers as well, because it feels like there's a sort of a fractal detail going on here that reminds me of how they work.
Yeah, possibly. We have a bunch of comments on our live stream here, which I haven't been looking at. Okay, let's take a look at this. Adjacency tensor under the continuum of a hypergraph on should give us smooth functions on Rn. I agree. Mixing category theory and graph theory sounds interesting, with categories being like a form of graphs themselves, a graph abstraction of graphs. Yeah, well, isn't that the life of higher category theory?
I mean, I've also been looking at this, and it turns out that quivers generate categories. Xerxes was telling me about this among other people.
Okay. Memes is asking, how is a quiver different from a sheaf? Do you have a quick answer to that, Tally?
I mean, they're very different. I don't know how to compare.
Okay.
Objects that are that different, but
Oh, Jimmy is offering us a nice piece of code for graph remove loose ends, which I think we already have basically a version of. Okay, I'll be asked, the digraph I have, every node is represented by a 1-bit output and a 4-bit input. The 4-bit input is the node label. After one configuration update, the updates done on the previous walk are the new inputs to the new walk or path. This represents the collapse problem. I don't entirely understand that. I mean, there's a version of these multiway graphs, which is the inverse collapse problem. Okay, continuum limit of the adjacency matrix, Alan asks or says, is defined by the infinitesimal limiting nature of the vertices. Not sure if the vertices approach 0, the matrix is regressive vertices. I don't know. Richard is saying how this ties into fusion categories and the fractional dimensionality investigation could be interesting.
Ah, fusion categories. They've come across them, and I know that I want to know more about them. Maybe Richard can reach out to me if he wants. If he knows about them.
Okay, this Richard is commenting natural extension limits to hypergraphs are considered by Alekan, who has done many graph theory things. Luis is saying try n-1 squared times n+1 cubed. Because of n plus x, the graph is not able to evenly distribute the addition, so segmentation, yes. Right. I don't see how this dimensionality of the symmetric measurable function is actually 2 to the k minus 2 for k uniform hypergraph. We're unlikely to get k uniform hypergraphs. I agree with that statement. But the question here is, okay, so let's look at the very simplest case where we get, so remember, in the case where that is a number, okay, what's the very trivial case? The very trivial case, if we do n+1, n+2, okay, we get a ladder. We always get a ladder. If we do n+1, n plus square root of 2, starting from whatever we want to start from, 0, we will get a tree, I believe. Oh yeah, we get a grid because of the commutativity of addition. Right. Makes sense, guys?
Makes sense.
Were we to do that with multiplication, we say n and n times square root of 2, we will also get a grid, he says. Oh no, because we get, okay, hold on. If we say n+1 square root of 2, what the heck is that? N times square root of 2, what the heck is that? What is that? Because if we apply square root of 2 twice, we get, okay, so that's essentially the square root of the previous pattern we had. That's kind of fun. So that pattern, right? So the claim would be, oh, that's kind of interesting actually, because that thing, well, that's interesting. I hadn't thought of that before. This is something where you get what's going on here. This is the square root of that previous thing, because you need to go 2 steps, but it has some much more complicated structure here.
Yeah.
I wonder what this does if we go longer. I mean, I wonder whether this has confluence properties too. And then we're going to try, okay, so this one here has some algebraic property. But the next thing I'm going to try is going to be absolutely hopeless. Let's see. Okay, so that creature, I don't know whether it's a very, let's just take a look at whether this is aquatic or not. Well, at least it could feed itself, maybe. I'm sorry, I'm not supposed to. That's a strange creature.
sea anemone
Yeah, right.
or
Okay.
some kind of kelp.
Okay, let's see. If we were to do this with pi, I claim, then nothing will close. It is a tree. So what we were seeing there were algebraic properties of root 2.
Yeah.
It's interesting. So I wonder if we were to do the same thing with like root 3, we would presumably see, I suspect we'd see something that is a little bit more tree-like. Oh boy.
I have to drop off now, but this was a fun session.
Thanks, Tally. Yeah, actually, I have to go to a different meeting very soon too.
Cheers, everyone.
Bye.
Bye.
Okay, anybody else got thoughts about this limit? I mean, so we've looked at some things with square root of 2 and so on, but what about the actual limit? Xerxes, maybe you have ideas about this.
I'm not sure. So are you planning to apply a graphon on this one or compute the graphon related to these things?
I don't know, because I don't know how to do the iteration with graphons.
Okay.
In other words, if we had a graphon, how would we iterate a graphon? Remember that we're trying to build a graphon. We're trying to build a multiway graph. That's different from saying we've got a hypergraph, which is a graphon, and how do we iterate that multiway graph? And clearly the continuity properties that we have in, I mean, our hypergraph, it's a big mess because the number of degrees of freedom of the hypergraph changes, which obviously to a graphon doesn't matter that much because the graphon is a continuous function anyway.
Mm-hmm.
But the question really is, yeah, so here's a question. If you think about things like, I don't know, stochastic calculus. Well, okay, so the analogies are stochastic calculus and path integrals, I think. Those are the two analogous situations where you're looking at limits of infinite numbers of paths. Does that make sense?
Mm-hmm.
So the question is, I don't know too much. I mean, as I recall, there are like trivial cases like binomial trees. Trying to remember. Pricing. Iteration, Richard says, would be like convolution. Yes, I agree. I'm looking at a random thing on the web here about stochastic calculus. I mean, the whole binomial tree I love the way this gets so directly into, okay, I mean, this is some random website that is talking about lattice models for pricing options and things, where you're looking at every time step. I mean, it is a similar situation. These binomial trees for, e.g., pricing. But there's a formulation of that in terms of stochastic calculus, which I suspect nobody on this call knows. Well, anyway.
All very interesting stuff.
Yes, except that I'm trying to finish the things I'm writing because I've got to get on to other things. And it's a trade-off between it's depth first search versus breadth first of all possible topics. And I'm also supposed to go and do a different meeting. Oh, it's actually live streamed as well. It's a design review for geography, astronomy, and date and time functions.
Ooh.
Okay, well, I think that's fun. Okay, Ed, do you have access to this file? I need to give it to you, and I need to give you this. And if you would have a chance to try, did you understand it? I'm not sure. I'm going to send these out. I mean, I think it will be useful to try to get that 30 times speed up on the search, unless there's some obvious other way to do it. Because that's the only thing I'm going to try to do is try to see whether we can get another couple of.
I put in a suggestion for a find walk function to go along with find path, find cycle.
Well, that's a good idea. Maybe somebody should prototype it though in the function repository.
Yeah, I'm going to try to.
Right, but so you should be able to just go. Let's see. I mean, it should be very straightforward. You should just apply all the rules, right? In other words, you've got the graph. From any given point, you simply apply all rules for the graph, and that gets you all the next points, right? It's really easy. And that's so what you need to do is just that.
Oh, okay.
See,
yeah,
I told you it was easy.
Yes.
Right.
I was thinking of something much more clever, but that's much better. Okay.
Okay. All right. I have to go, but to people who are interested, I'm about to do another live stream about an utterly different topic. So thanks to everybody here, and talk to you all soon.